The last crew member died on day 4712, not from an explosion, not from a hull breach or a catastrophic systems failure, from something we had identified, studied, and failed to solve since the earliest days of human spaceflight. Something we knew was coming, something we sent them into anyway. That scenario isn't science fiction, it's a projection built from real data, real biology, and real physics. And when you trace the math on a crewed mission to Proxima Centauri B, the closest potentially Earth-like world we've ever found, you don't end up with an inspiring story about human perseverance. You end up with a blueprint for extinction. Proxima Centauri B sits 4.24 light-years from Earth. That number sounds almost manageable. 4.24. You've driven farther than that in a road trip. But a light-year is the distance light travels in a full year, moving at 186,000 miles per second. In the time it takes you to read this sentence, light has already circled the Earth more than twice. In 1 year, it covers nearly 6 trillion miles. Multiply that by 4.24, and you get a number so large it stops feeling like a number and starts feeling like an insult. To put it in terms that actually land, if you shrunk the distance from Earth to the Moon down to 1 inch, Proxima B would be roughly 2.5 miles away. The Moon feels close. 2.5 miles of inch-scaled space does not. And this is the nearest one. This is the neighbour. Every other potentially habitable world we've catalogued is orders of magnitude further, so if we can't reach the closest option, we can't reach any of them. Proxima B is the test case, and the test case is brutal. The dream, to be fair, is a compelling one. A second Earth. A rocky, roughly Earth-sized world orbiting within the habitable zone of its star, where liquid water could theoretically exist on the surface. Scientists have detected it, modelled it, debated whether its atmosphere could support life, and somewhere in the cultural imagination, fed by decades of science fiction, by the speeches of visionaries, by the quiet terror of knowing we've damaged the only planet we have, the idea took hold that Proxima B could be a lifeboat, a continuation, proof that humanity doesn't have to end here. It's not an irrational dream. It comes from the same impulse that drove our ancestors across oceans in wooden boats, the same restlessness that put footprints on the Moon. We are a species that moves, and the stars feel like the next horizon. But the horizon, in this case, is not across an ocean. It's across a void that doesn't care whether you survive it. With the fastest spacecraft humanity has ever launched, the Parker Solar Probe, which reached speeds approaching 430,000 miles per hour during close solar passes, a trip to Proxima B would take approximately 6,300 years. That's not a typo. 6,300 years. The pyramids of Giza were built roughly 4,500 years ago. We would need to sustain a functioning, self-replicating human civilization inside a sealed metal container for longer than recorded history before anyone arrived. Voyager 1, our furthest flung spacecraft, has been traveling since 1977 and has barely made it out of our own solar neighborhood. At its current speed, it would take over 70,000 years to reach Proxima Centauri, if it were even pointed in the right direction, which it isn't. These are not pessimistic estimates. These are the numbers. So the obvious question is, what if we go faster? What if we build something better? Physicists and engineers have spent decades on this. The proposals are genuinely fascinating and genuinely sobering. Nuclear pulse propulsion, detonating a series of nuclear bombs behind the ship to generate thrust, could theoretically reach 1 to 5% of the speed of light. At 1%, the trip still takes over 400 years. At 5%, you're down to around 85 years, still longer than a human lifespan, but now we're at least in the territory of generational ships. Antimatter drives could, in theory, push a vessel to 20 or 30% of light speed. The problem is producing antimatter. We currently generate it in particle accelerators at a rate of a few nanograms per year. To fuel an interstellar mission, you'd need grams, possibly kilograms of it. Producing that quantity with current technology would take longer than the age of the universe and cost more than every economy on Earth combined, indefinitely. The energy required isn't just beyond our infrastructure, it's beyond the scale of anything our civilization has ever attempted. Laser sail concepts like Breakthrough Starshot propose sending postage stamp-sized probes to 20% of light speed using Earth-based lasers. That's remarkable for a probe. For a crewed vessel carrying enough life support, food, water, spare parts, medical equipment, and shielding to keep humans alive for decades, the mass requirements make the laser array needed essentially a continental scar. The engineering project producing more power than most nations currently generate, and we haven't even discussed what happens when you need to slow down at the other end because laser sails only accelerate. Deceleration requires something waiting for you at Proxima. Nothing is. But set all of that aside. Assume, generously, that we solve propulsion. Assume some breakthrough physics delivers a ship capable of reaching 10% of light speed. The trip takes 42 years. A crew of, say, 20 to 40 people, sealed inside a vessel, with no resupply, no rescue, no real communication. Signals would take 4.24 years to arrive back on Earth, and another 4.24 to return. Begins the journey. And that's when the human body starts working against you. Within the first few months, bone density begins to drop. In microgravity, the skeletal system receives no load-bearing signals and begins reabsorbing calcium. Astronauts on the International Space Station lose 1 to 2% of bone mass per month in key load-bearing areas. In 6 months, that's the bone density profile of someone decades older. In a year, fracture risk becomes serious. In 4 decades of travel, you are not dealing with weakened bones. You are dealing with a crew that may be structurally unable to stand, walk, or survive the physical demands of landing operations, assuming a habitable surface is even waiting for them. Muscle atrophy follows the same curve. Without gravity, the large postural muscles of the legs, lower back, and core have no reason to maintain their mass. The heart, a muscle, also shrinks. Blood redistributes toward the upper body, causing chronic fluid pressure in the skull and against the optic nerves. Astronauts returning from 6-month ISS missions have documented measurable changes to the shape of their eyeballs. The optic nerve sheaths swell, the globes flatten slightly, and some develop permanent vision impairment. On a 42-year mission with no gravity and no way to reverse these changes, crew members would likely arrive with severe, irreversible vision loss. Some would arrive blind. Then there's radiation. Inside Earth's magnetic field and atmosphere, we are largely shielded from galactic cosmic rays, high-energy particles traveling at near-light speed, originating from supernova remnants and other extreme cosmic events. In deep space, that shielding is gone. These particles don't just pass through the body, they ionize tissue, shatter DNA strands, damage the central nervous system at the cellular level. Shielding helps but adds mass, which is already the enemy of propulsion, and no shielding we currently know how to build eliminates the risk entirely. Lifetime radiation doses that NASA considers acceptable would be exceeded within the first few years of an interstellar cruise. Over 4 decades, the cumulative exposure translates to near-certain cancer, likely neurological degradation, and potentially heritable genetic damage that would compromise any children born on the voyage, the next generation of crew members who never consented to any of this. And this is where the mission stops being a tragedy and starts becoming something else, because a generational ship isn't just a vessel, it's a civilization. It requires births, deaths, child-rearing, education, governance, conflict resolution, and psychological stability across decades in an enclosed space the size of a large building. Psychological research on isolation, Antarctic overwinter stations, submarine crews, simulated Mars habitats, consistently shows that cognitive performance degrades, interpersonal conflict escalates, and depression and anxiety become endemic after months, not years. We are not built for permanent enclosure. We are not built for the absence of a horizon, natural light, open air, or the basic sensory variety that keeps human minds functional. One system's failure compounds another. A water recycling malfunction forces rationing, which stresses crew health, which impairs the decision-making needed to fix the system. A radiation event damages electronics and simultaneously delivers a dose to the crew. Repairs require spacewalks, which expose the crew to more radiation. Medical emergencies arise that require surgery, which requires a functioning surgeon who is also aging, also irradiated, also suffering the same biological degradation as everyone else. Spare parts run out, knowledge erodes across generations. The mission plan, designed by people now 4 light years away and 40 years dead, may no longer match the reality inside the ship. This is not a string of unlikely disasters. This is the expected trajectory, derived from what we already know about biology, physics, and human psychology. The extinction scenario in the title isn't hypothetical catastrophizing. It's the realistic outcome of sending a small, isolated, biologically fragile population on a multi-decade voyage through an environment every system in their body was designed to never encounter. With the tools and understanding we currently possess, a crewed mission to Proxima B does not fail at the engineering stage. It fails at the human stage, and that failure isn't a problem waiting for a clever solution. It is a consequence of physics and biology operating exactly as they're supposed to. We are creatures of one atmosphere of pressure, one gravity well, one magnetic shield, one star's worth of radiation at a very specific distance. We evolved inside a remarkable set of conditions that exist, as far as we know, in only one place within reach. Stepping outside them doesn't just challenge us, it dismantles us, slowly and completely. But here's what that doesn't take away. We looked up at a star 4.24 light-years away and we found a planet. We measured its orbit, we calculated its mass. We modelled its possible surface conditions from here, from this small rock we can't seem to leave, using mathematics and instruments and the kind of relentless curiosity that has no obvious survival advantage and yet persists in us anyway. We can see Proxima B without ever going there. We can understand it. We can name it. That's not nothing. In a universe this large, in a cosmos this indifferent, a species that can reach across light years with its mind, but even when its body a note follow, is doing something genuinely remarkable. We may not touch that world, but we found it.